Hello everyone, I am sure you are all having excellent time. It gives me an immense pleasure to welcome you all to my third NPTEL lecture series. This is on interpretive spectroscopy. This is a lecture series of 60 lectures. Okay, so this is the first lecture. This is, as I mentioned, this is about interpretative spectroscopy. So what I would do is, in next 60 lectures, I will be discussing about some of the very important spectroscopic methods such as NMR, IR, UV visible, EPR, and also mass spectrometry and mass bar spectroscopy. So in this one, as I already told in the introduction, without going deep into the theoretical aspects but giving some fundamentals and basics, I would try to make you familiar with the interpretation and elucidation of the structure. So with this, let me start my first lecture. So the spectroscopic methods are also comes under analytical chemistry. So what is the role of analytical chemistry? So analytical chemistry involves measuring the chemical composition of natural and synthetic materials. Analytical techniques are essentially used to identify the substances which may be present in a material and determine the exact amount of the identified substances. That means it involves both qualitative and quantitative analysis of an unknown sample or samples obtained from natural resources. Or it can also be mentioned in a different context, the resolution of a chemical compound and its proximate or ultimate parts, that is the determination of its elements or of the minor impurities, byproducts or substances it may contain. So that means to know how pure the sample is and what are the composites of that one and also what are the constituent elements. So all these details would come from analytical chemistry, and spectroscopy is a branch of one of the analytical methods. So how to classify these analytical methods? We can classify broadly into two methods. One is qualitative analysis. The second one is quantitative analysis. What is qualitative method? It provides information about the identity of atomic or molecular species or the functional groups present in the sample that we are analyzing. That means the determination of the components of an unknown sample. So how we do it? We can go for, the best way is to go for spectroscopic methods. And what is quantitative method? In contrast to qualitative method, it gives numerical information as to the relative amounts of one or more of these components. Unless we know what it is not advisable to go for quantitative method, or quantitative method is of little use unless we know what it is. So from that point of view, qualitative method is very important, and once after knowing what the substance is to quantify, we should go for an appropriate quantitative method. So that means the determination of the quantity of the component in a sample. So how to do it? We can do it in several methods. I would come back to that one. The separation of analytes by using one of the methods we use, like precipitation, extraction or distillation. And qualitative analysis means reaction. How we do qualitative analysis? By reacting analytes with reagents that yielded products that could be recognized by their color, boiling or melting points, or solubilities, optical activities or refractive indexes if they are optically active compounds. Quantitative analysis can be performed by either gravimetric or titrimetric methods. What is gravimetric method? Determination of the mass of the analyte or some compound produced from the analyte. So in titrimetric method, what we do is we will measure the volume or mass of a standard reagent required to react completely with the analyte. So indirectly we will be knowing the quantity of the substance. This is a typical analytical arrangement or analytical instrument. Whether you take analytical instrument or spectroscopic instrument, some of these things are imbibed in the instrument. So first we have to look for a right signal source, and then we have to put the sample, and then the signal, the electromagnetic passes through that one, and then we will be having signal analyzer, and then signal detector and transducer, will be there, and then it will be fed to data processor, and then eventually we get the result. So this is how the components work in a typical instrument. Then let us try to classify different type of analytical methods and what we are going to get from those methods. So gravimetric method, so weight of pure analyte or of a stoichiometric compound containing it, and volumetric, volume of standard reagent solution reacting with the analyte. In spectrometric, intensity of electromagnetic radiation emitted or absorbed by the analyte, the unknown sample, and radiochemical, intensity of nuclear radiation emitted by the analyte. And in mass spectrometry, abundance of molecular fragments derived from the analyte along with the molecular mass. And chromatographic method, its physicochemical properties of individual analytes after separation, and in case of thermal method, physicochemical properties of the sample as it is heated and cooled. What would happen to a sample with temperature variation? So then where exactly we use it? In fact, in all disciplines of science we use it: chemistry, physics, biochemistry, medicine, forensic materials. In case of chemistry, invariably it is used in inorganic chemistry, organic chemistry, as well as physical chemistry. Then what are the applications? The first one and at most important one is fundamental research. That means we always make new molecules, and then or we look for analysis of natural products or drugs. And in product development in industries and pharmaceutical companies and material related companies, development of alloys, polymer composites, resins or new materials, and also in industries, product quality control, analysis of raw materials and finished products. So this is where analytical instruments are heavily used. And what are the applications? Yes, monitoring and control of pollutants, very, very important. That means heavy metals and pesticides, contamination. And then the metal content of ores, how much quantity of metal is there in a given ore, whether it is worth extracting or economical. And medical and clinical studies, indicators of physiological disorders, and in food analysis, and also labeling and origin. So then that means these analytical techniques and chemical analysis is an indispensable component of modern technology, and always these two components have developed hand in hand. So here the analytical techniques can be classified again as classical techniques, instrumental techniques, and historically derived and artificial ones. Artificial problems and their solutions comes from analytical methods. For all analytical problems, the solutions, whether qualitative or quantitative, follow the same basic pattern which can be described using 7 entities. What are those 7 entities? Yes, first the choice of the method. So after having an unknown sample in hand and also the nature of the sample or from which this source sample has obtained, we have to choose a right method. So choice of the method is very, very important. For example, if we take organic molecules, first thing we should do is we should go for NMR, and then to know it, mass spectrometry like that. But sampling is equally important. How to prepare the sample for different instrument, and preliminary sample treatment is also important, and then separation and components has to be separated, and final measurement has to be made, and method of validation has to be looked into it, and then eventually elucidation, assessment of the results and elucidation of the structure. So these are all fundamental the entities one should look for while using analytical methods to analyze unknown samples. And instrumental methods, the measurements of physical properties of analytes such as conductivity, electrode potential, light absorption or emission, mass to charge ratio, and fluorescence are essential in the quantitative analysis of a variety of organic, inorganic, organometallic and biochemical analyte. Then instrumentation is divided into 2 categories. One is first detection and then quantitation. And some of these units one should be familiar with. We extensively use ppm, this parts per million, and ppb, parts per billion. Apart from those, we also use some of these units such as giga, mega, kilo, deci, centi, milli, micro, nano, pico, femto, and atto. So we should know the symbols and also corresponding units, like giga is 10 raised to 9, whereas atto is 10 raised to minus 18. So we should be familiar with these terms. And then in different instruments, energy is presented in a different form. For example, it can be Hartree, electron volts, centimeter minus, kilocalories per mole or kilojoules per mole, or degree Kelvin, or joules, or even hertz. So this table gives the conversion of one unit into another one very nicely. And then what are the objectives of analytical chemistry? First thing is to know what the sample we have in our hand, that means identification and qualitative analysis. These two are very important. First we have to identify the substance, and then we have to do qualitative analysis to know what it is, and then to know how much it is we have to go for quantitative analysis. And then spectral interpretation follows this pattern here. You can see once we have pure compound in hand, we can use several instruments at our disposal to know what it is. For example, we can see CHN, MS and NMR. We can use that, would give you molecular formula, and if you go through NMR, IR and UV, you can identify functional groups, and if you go for NMR, it can tell you about substructures. For example, if you take ethanol is there, it can easily tell there is a methyl group, methylene group and OH group, or a amine is there, you can say there is an NH2 group or NH group or N group. And of course, X-ray would come at the end, and then molecular formula is there, and then we can use hydrogen deficiency index. Of course, even with the mass, when we see molecular ion peak, we can also arrive at molecular formula using rule 13. And then once we tentatively come up with a molecular formula, we can look into unsaturation using hydrogen deficiency index, and then we can write possible structures getting information from these methods. And then once we have structural formula, we can start writing all possible isomers, and then we can also write all possible structures. And then once when you go back to again NMR, mass, IR, we can arrive at the precise most possible or the most correct structure. And then with this one again, if we analyze through NMR, we can give reasonable structure. And of course, if it is a solid sample and if you could get the structure, we can, using X-ray diffraction, we can tell the correct molecular structure of the substance. So known molecular formula. So this is how we revolve around these spectral methods to interpret and elucidate the structure of a new substance. Now, how to approach spectroscopic method for structure, and who does this one? Synthetic chemists, biological chemists, natural product chemists, forensic chemists, environmental chemists. So then how can I determine the structure of the molecule? Yes, there are several steps one should follow to identify new chemical compounds and mechanism of biochemical processes, natural products from plants and animals, drugs, toxins and explosives, materials containing soil, water or the atmosphere. In all these things, we use extensively to identify the sample, identify the right kind of chemicals. So, the spectroscopic approach follows this pattern. To identify molecules, one can use an array of structural information extracted by all these spectroscopic methods. It is possible to get the information as rapidly as possible, and one can deal with all phases of matter, mixtures and pure components. That is the strength of these methods. Many spectroscopic methods will provide you ways to analyze the sample in their own state, whether it's solid, liquid or gaseous. The process of determining structure is very deductive and is much like solving the puzzles. One or more spectroscopic experiments have to be carried out, and by analyzing the data, we can hopefully determine the correct structure. The most common methods for structure determining at present we are using are mass spectrometry, nuclear magnetic resonance spectroscopy, electron paramagnetic resonance or electron spin resonance, infrared spectroscopy, and electronic spectroscopy and mass bar spectroscopy. Each method provides its own special kind of data that we can apply to molecular structure determination. And then here we should also know about approximate time scale we come across with different techniques for structure determination. For example, electron diffraction, 10 raised to minus 20. Whether you consider X-ray as mass bar, it comes around 10 raised to minus 18. So that means whatever the process that happens up to that 10 raised to minus 9 can be detected using these techniques. And then it drops here, UV visible 10 raised to minus 15 and visible 10 raised to minus 14, IR and Raman 10 raised to minus 13, ESR is 10 raised to minus 4 to 10 raised to minus 8, and NMR 10 raised to minus 1 to 10 raised to minus 9. If any dynamic process that's happening in the molecule beyond this one, say much slower than 10 raised to minus or faster than 10 raised to minus 9 cannot be detected. In that case, we should have to alter those. How to alter? By raising the temperature or by cooling the temperature of the substance. Fast kinetics 10 raised to minus 3 to 10 raised to 2, and physical separation, at least they should be stable for 100 seconds for doing physical separation. And then the different type of electromagnetic radiation we use in the different instruments is shown here. For example, microwave where we use it, and then microwave we use, and radio waves we are using, infrared we are using, visible light, ultraviolet, X-ray and gamma we use in mass bar spectroscopy. And then this can tell you where exactly this radiation is used. In NMR we use here, and EPR we use microwave, and also in rotation spectroscopy, far infrared and vibration spectroscopy, and near infrared to vacuum we use UV visible spectroscopy and also photoelectron spectroscopy, and then this is X-ray, and then gamma rays we use in case of mass bar spectroscopy for looking into nuclear transitions. And this is the NMR periodic table that gives a lot of information about NMR active nuclei present in various elements as isotopes. Some of them may be 100%, some of them may be less, and some of them have I equals half or 3 by 2, or some of them have I equals 1, 3. All this information is given here. So another beautiful periodic table is there that shows right here I equals half, this yellow is 3 by 2, and then orange is 1. So that means most of the elements we see in the periodic table can be analyzed through NMR, and multi-probe NMR are quite common nowadays. We can do NMR for any of these elements shown here with non-zero nuclear spin value. And this gives about information about different isotopes. So this also very good. It helps in analyzing using mass spectrometry, looking into the mass fragments, whether we get M plus 1, M plus 2, M plus 4. All this comes simply by looking into what kind of elements present and how many isotopes are there, and ratio. All those things is quite helpful in interpreting the data obtained from mass spectra. And then of course elemental, we can also get information from mass bar technique. Apart from iron that is extensively used, we can also use some of those things shown in the red using mass bar technique. In the contribution from different form of spectroscopy should be looked into it. And here nuclear magnetic resonance spectroscopy is very popular among not only organic and inorganic chemists, organometallic chemists, and also biochemists. It is quite useful, and pharmaceutical industries it is heavily used. NMR experiments apply to nuclei that have the quantum mechanical properties of the spin. For example, if you think nuclear spin I equals half, we have several very well known ones, 1H, 13C, 31P, 15N, or with 1 is 2H and 14N, and also we have many 3 by 2 boron 11, and also boron 10 has 3. And NMR provides information about the types, numbers and connectivity of a particular atom. For example, NMR can show, if you just look into NMR spectrum of ethanol, it can tell you it has CH3 group, it has CH2 group, and also it has one OH. That means it can also tell you that there are 2 types of carbon in the ratio 1:1, and 3 types of hydrogen atoms are there in 3:2:1 ratio, and CH3 and CH2 groups are bonded together, and CH2 is connected to OH. All this information comes very nicely from the 1H NMR spectrum of ethanol. Similarly, for isopropanol, if you look into it, it shows that 2 CH3 groups are there and 1 CH group is there, and then OH is there. So it will tell you about isopropanol. And then if you take normal propane, it can tell you that 1 CH3 is there, next to that there is 1 CH2 is there, next to that there is one more CH2 is there, and that is connected to OH. So that means it can give you almost precise information provided we know how to interpret and elucidate the structure. For many molecules, the entire structure can be deduced no matter how complicated it is, provided it is in its purest form. And routine NMR experiments are performed in solutions of the molecules dissolved in deuterated solvents. such as CdCl3, C6D6 and D2O using a few milligrams of samples. Of course, how much quantity of sample we should use also depends on the abundance of the isotope. For example, 1H is 100%, 31P is 100%, 19F is 100%, small quantity is sufficient, whereas in case of 13C we have only 1.1%, we need substantially more amount of sample. NMR can be used to study mechanisms for intermediates of chemical reactions in solution and also to monitor using NMR, especially 31P NMR, if you are using a phosphine or a phosphorus based compounds in a homogeneous catalysis for a particular organic transformation. The sample may be mixtures. NMR is a very general method, but it is most useful spectroscopic approach for determining the structures, especially when you have organic samples or even inorganic material in it. And infrared spectroscopy is equally important. IR spectra result from the absorption of infrared radiation that causes vibrations of the molecules. That means if you look into a diatomic molecule and it's not a rigid, the bond can be stretched, okay, bond can be bent, bond can be waggled, so all kind of things happens. So that can be monitored using simply passing infrared radiation over a molecule in a proper way. The spectra are typically presented as percentage transmittance or absorption. The peaks carry information such as functional group identification, structure information and even symmetry. IR is a very sensitive method and is used widespread in part due to its easy sample preparation, and also equipment is not at all expensive and compact and simple to use, that a single spectrum can be run in just a few minutes. The presence of functional groups give rise to distinct features that can be identified within well-defined range of the spectrum, but IR is only limited to determining the presence and identification of functional groups. No, but it cannot tell you how many groups are there. Sometimes it can tell you or how much it is there. All this information you cannot get it, but you can identify the presence of those functional groups. So in case of NMR, the energy difference is proportional to the magnetic field strength. That is very simple. And of course, what we do is we take a nuclei, keep it in a magnetic field. When we start keeping in a magnetic field, what happens? Some of them will be aligned with the magnetic field, some of them will be opposing the magnetic field, and they start precessing with respect to the magnetic field. So when they are precessing, the frequency with which they precess is called Larmor frequency. So since it is angular, it is not nu, it is omega. Omega equals 2 pi nu. So omega equals 2 pi nu. Therefore, if you take nu, then it will be 1 over 2 pi, and this Larmor frequency is directly proportional to the applied magnetic field. And then we bring a constant that is called gyromagnetic ratio. And then once if you want to look into the frequency will be gamma over 2 pi into B naught. So that's a very simple equation one should remember, and gamma is very unique for each nucleus. It is called gyromagnetic ratio. For example, in case of hydrogen, it is 26.753 radians per Tesla per second, and that means in a 14,092 Gauss field, a 60 megahertz proton is required to flip a proton. So that means you have to apply a radio frequency of 60 megahertz in a direction perpendicular to the applied magnetic field to flip the proton or to see the transition, spin excitation. That means the 60 megahertz is equal to the Larmor frequency of that nucleus, and this comes in the low energy radio frequency. And then this can show you different type of stretching modes, for example symmetric stretching modes, or it is antisymmetric, and then this is called scissoring, and this is called rocking, and this is called wagging, this kind of twisting. So all kind of these vibrational motions can be assessed using IR spectroscopy. As I mentioned, they behave like two spheres attached by a spring. And then what the equation, we should remember only one equation. Then how to correlate this vibrational frequency can be correlated with the reduced mass of two atoms between which that bond is there, and also the force constant. So here we can use, this is the fundamental one, this is simplified to 130.3 into square root of f over mu, or it can be mu equals 4.12 into square root of f over mu, where f is the force constant and mu is the reduced mass. Reduced mass will be m1 m2 over m1 plus m2, where m1 m2 are the two atoms that is holding in the diatomic species. So that means by knowing the force constant, we can predict the stretching force, stretching frequency, or if you know the stretching frequency, the corresponding force constant can be determined. For example, here I have given reduced mass for this OH combination and NH various bonds, and also force constant is also given and frequency is also given. You can use these equations to verify whether this data is correct or not. Then when it comes to UV spectroscopy, what we should remember is we should remember only simple Beer-Lambert's equation, A equals log 10 into I naught over I, that's equal to epsilon CL. Is a longer path length 1 L through the sample will cause more UV light to be absorbed. The greater the concentration of the sample, the more UV light will be absorbed, and UV visible spectrum consists of absorbance A on y axis and wavelength on the horizontal x axis. The number of arrangements of electrons in a given subshell for a given electronic configuration, especially when you go to transition metals, that is called microstates. According to Hund's rule, what happens? Ground state will be having all, for example, 3 electrons are there in d orbital, all will be singly occupied up to 5. The 6th one will be getting paired. Whereas when we look into excited states, we can have all different possibilities. That how many such different possibilities are there for arrangement of the electrons comes from the number of microstates, that is given by n factorial over r factorial into n minus r factorial, where n is the capacity of the subshell. That is, for example, d is 10 factorial, f is 14 factorial, and p is 6 factorial. And if you take s orbital, it is 2 factorial. And n is the total number of orbitals in a subshell, or total electron capacity, or L equals azimuthal quantum number, and R is the number of electrons in the subshell. D7 means it is 10 factorial, it is 7 factorial. And then the different type of electronic transitions anticipated is shown here. For example, we have sigma, pi bonding, n, and then pi star and sigma star. Whatever happens, the transition should happen between these, and the corresponding energies also you can assess from here, and sigma to sigma star is much greater than, because they are farther, and then to n to sigma star, and then pi to pi star, and the n to pi star. So these are all unoccupied levels, and these are all occupied levels. So and whatever the highest occupied molecular orbital and lowest unoccupied molecular orbital, we call them. And then where exactly we see this kind of transition also seen here, sigma to sigma star in alkanes, sigma to pi star in carbonyls, pi to pi star unsaturated compounds, and n to sigma star is ONS halogens, and then n to pi star in carbonyls. And DD transition is another one that we see in case of transition metals. And then what is the rule of 13? So for example, we get molecular mass in a spectrum that gives a number. From that number, we should approximately get an idea about what are the, of course, before that we should know what are the elements present in it. Once if you know what are the elements present in it, we can come up with a tentative molecular formula. So that is done by this rule of 13. What we do is take this m plus and divide by 13. This gives a quotient and remainder. And then the quotient will be number of carbon atoms, and quotient plus remainder will be number of hydrogen atoms. And then what happens, for example, you take m plus is 78, and 78 divided by 13 is 6. This is n, and there is no remainder, so n is 6, so C6H6, this is benzene. And if you take 161, what happens if you divide 161 by 13, we get 5 as remainder, and then if you add 5, it becomes 12 plus 5, 17, so it becomes C12H7. But if you have, say, other heteroatoms, what you can do is, for example, n is there, n atomic number is, atomic weight is 14, so you can take CH2, or if you take oxygen CH4, like that, you start eliminating those groups, and you can add this one so that you can get the corresponding molecular formula. And then of course NMR, multinuclear NMR is very interesting. For example, if you see here this molecule, we have 1, 2, 3, 4, 5 different NMR active nuclei are there, 19F, 31P, 15N, 1H, and also 29 silicon. For example, here one spectrum I have shown here, 31P NMR, how it looks. First it splits into a triplet because phosphorus to fluorine coupling is very strong, and then it is each triplet line is split into a doublet. This is called splitting tree, into a doublet, because I equals half. All those things I will be elaborating when I start digging into NMR spectroscopy. And then next it comes H, it will split further these signals into a doublet here, and then eventually these 3 protons would split this into 2n S plus 1 4 lines, so we are getting this beautiful 48 lines. And then you can see very nice spectrum we get this one. Like this, many interesting molecules are there, and not only NMR, we also saw a lot of problems in IR and also in UV visible and also mass spectrometry and also EPR. So let us start making ourselves familiar with interpretation of data obtained from different spectroscopic methods and the elucidation of the structure. So see you all in my next lecture. So I will begin my next lecture with NMR. I wish you all the very best and see you soon. Thank you.